This is session C3, Particle in a Box, Part 1. Last session, C2, we did Schrodinger Equation and energy values. We covered the time-dependent and time-independent Schrodinger Equation for spatial problems and spin problems. We said that the time-independent Schrodinger equation has energy eigenvalues and energy eigenfunctions. Everything that we looked at abstractly in the last lecture, we will look at concretely in this next series of lectures for a single spatial problem called particle in a box. When I first learned particle in a box, I didn't see the point and I gave it no respect. I was in a hurry to get to the hydrogen atom. Now I understand that we can use particle in a box to learn a lot practically about the Schrodinger equation and its solutions without needing much math or physics, but also that we can learn something about the energies of real practical systems. Particle in a box is the simplest possible spatial bound system. The math is simple, so I want to cover this problem fully to help you learn quantum mechanics. This lecture is only part 1 for particle in a box. The free particle in one dimension that we used in lecture C1 is the simplest possible spatial problem that is unbound. Its energies were continuous, not quantized. Particle in a box in one dimension, also known as the infinite square well, is the simplest possible spatial problem that is bound. Its allowed energies will be discrete or quantized. This is a spatial problem, so we need to specify the potential energy function for this particle in this system. The potential energy function expresses the system in which the particle exists, is located, and might possibly move. For a free particle, we had that the potential V of x was everywhere 0. For the particle in a box in one dimension, we have 3 regions of space. For x less than 0, the potential is plus infinity. For x between 0 and a, the potential is 0. For x greater than a, the potential is plus infinity. This potential specifies the box, or the well, that this particle is in. Now, we are free to use any energy value for the potential energy within the box, the region 0 to a. 0 is the most convenient energy value to choose. Energy eigenvalues for this problem will be relative to this 0 energy level. If you object to the infinite values, consider them to be arbitrarily high, finite, positive values. We say that there are hard walls at x equals 0 and x equals a, and the particle cannot exist, it never exists, in the regions beyond the hard walls, x less than 0 and x greater than a, which are completely forbidden regions. We show the potential energy graphically this way. Beyond the walls at 0 and a, we show a cross-hatching. Graphically, that means that it's a hard wall and the particle cannot go beyond the hard wall. This is a possible time to take a break. This potential energy is a real valued function of x, and it's independent of time. The Hamiltonian for this one-dimensional system is independent of time. H hat equals the kinetic energy term minus h bar squared over 2m partial derivative, the second partial derivative with respect to x squared. I should have shown this as partial derivative, plus the potential energy V of x that we identified previously, where m is the mass of the particle that is in the box. And I've replaced the partial derivative with the ordinary derivative ddx because I'm going to use the time-independent Schrodinger equation. But it should have been a partial in the Hamiltonian. Since this Hamiltonian for this problem is independent of time, we can use the time-independent Schrodinger equation from last lecture. And we can find the energy eigenvalues and energy eigenfunctions for the energy eigenstates for this particle in this box. So the time-independent Schrodinger equation is h psi equals E psi, where this psi is lowercase because it's going to be independent of time but dependent on space. And I'm using the subscripts n because I'm expecting that there will be multiple possible eigenvalues and eigenfunctions. So E sub n is one of the real valued energy eigenvalues that solves this particular Hamiltonian for this particle in a box system. And lowercase psi sub n of x is one of the energy eigenfunctions that, with energy eigenvalue E sub n, solves this particular Hamiltonian for this system. We say that this state is an energy eigenstate. Let's start with the region x less than 0, for which the potential was plus infinity. And so the Hamiltonian is plus infinity, or an arbitrarily high positive value. In quantum mechanics, wave functions always, or only ever, have finite values at every point in space and at every time. So psi sub n of x must be finite. Energy eigenvalues must also be finite. So the right-hand side of the time-independent Schrodinger equation must be finite. It's E times psi, and each of those is finite. Since the Hamiltonian is plus infinity, or an arbitrarily high positive value, the only way that the left-hand side, h psi, for x less than 0, can remain finite is if psi sub n for x less than 0 is identically 0, exactly 0. Then h psi would be 0 and e psi would be 0, so the equation would be true, both sides would be 0, so it is an equality. Now, if you object to multiplying infinity times 0, which you should, don't think of psi as infinity, think of it as any arbitrarily high positive value. Then when you multiply it by 0, it is 0. So don't get hung up on the plus infinity. Think of it as the largest number that you can imagine instead of infinity. So psi sub n equals 0 solves the time-independent Schrodinger equation in this region, x less than 0, independent of any energy value E sub n. Solving it did not put any constraints on E sub n. Now we also have a hard wall at x equals a, so likewise we require that psi sub n for x greater than a be identically 0. This is a possible time to take a break. So we've solved two regions. Now we have to solve the middle region, 0 to a, the actual well, the inside of the box. The forbidden regions impose no constraint on the energy eigenvalues. We assume that we will get energy eigenvalues due to the center region. We'll see that. So we need to solve h psi equals e psi, where h is the kinetic energy term minus h bar squared over 2m, second partial with respect to x squared, plus potential energy, but the potential energy is 0 in this center section, inside the box. So that's all we have is the kinetic energy term, times psi equals e psi, inside the box. We can rearrange this as follows, putting everything on the left side. Now we can use ordinary derivatives because there's no time involved in this equation. Second partial derivative of psi with respect to x plus 2 times the mass times the energy eigenvalue E sub n divided by h bar squared times psi sub n equals 0 between 0 and a, inside the box. In quantum mechanics, for spatial problems, the lowest value of energy eigenvalue cannot be lower, less positive, more negative than the lowest value of potential energy for all space, which in this case is 0. So E sub n is going to be greater than or equal to 0 for this particle in a box. Therefore, the term 2 times mass times energy over h bar squared is going to be greater than or equal to 0. And therefore, it could be expressed as the square of a real number. And we're going to do that. We'll write the real number as wave number k sub n. So wave number k sub n squared is 2 times the mass times the energy over h bar squared. Once we know energy and wave number, this will be true. This is we're defining the wave number. When we substitute that in, we get a second order ordinary differential equation of a very simple common form. Second derivative of psi plus k squared psi equals 0, again within the box. And once we know the wave number k that solves this equation, the energy will be h bar squared k squared over 2m. This is the ordinary differential equation for sinusoidal motion, whose general solution we can choose to write as a cosine k sub n x plus b sine k sub n x between 0 and a. We could also have chosen to written it in terms of complex exponentials, but here the most useful form will be to write it in terms of sines and cosines. Now, if you want, you can verify that if we take the second derivative of this psi, we get minus k sub n squared psi. And if we plug that back in, we get that the left-hand side is 0 and the right-hand side is 0. So it does solve the time-independent Schrodinger equation in this region. This should say TISE. This is a possible time to take a break. To complete the solution, we must use boundary conditions at the boundary of the box, the hard walls. Right now, we have arbitrary constant A and arbitrary constant B, and we have not matched up the region within the box with the regions outside the box, and we need to do that. In quantum mechanics, for spatial problems, wave functions psi of x, y, and z and capital psi of x, y, z, and t must be continuous functions of the spatial coordinates, even at hard walls and at potential energy impulse functions, which we're not going to talk about. There cannot be spatial discontinuities in wave functions. So, psi sub x must be continuous at x equals 0, even though the potential energy is discontinuous there. Not only discontinuous, it's 0 on one side and infinite on the other. From the infinite potential energy for x less than 0, we determine that psi must be exactly 0 when x is less than 0. For continuity, we must have that psi must be 0 at x equals 0, and psi must be 0 for x equals 0 plus, infinitesimally close to x equals 0 coming from above. Therefore, psi sub n of x must approach 0 as x approaches 0 from above. This eliminates the cosine term. Cosine of 0 would be 1, and we need the psi to approach 0. So the cosine term is gone. Now we're left with psi sub n of x equals b times sine of k sub n of x inside the box. Now, there are two unknowns here. B is an unknown, but also k sub n is an unknown. We don't know if it can take on any value whatsoever, or if its values will be restricted. We need to learn that. Psi sub x must also be continuous at x equals a, another hard wall, even though the potential energy is discontinuous there. From the infinite potential for x greater than a, we determine that psi equals 0 for x greater than a. For continuity, we must have that psi equals 0 at x equals a, and that psi must be 0 for x equals a minus, infinitesimally close to x equals a coming from below. Therefore, psi sub n of x must approach 0 as x approaches a from below, which we can write as psi sub n of a equals b times sine of k sub n times a. That must equal 0. We achieve this if and only if the argument of the sign, k sub n times a, equals any integer times pi. So n times pi, where n is any integer from 0, 1, 2 to plus infinity, but also 0, minus 1, minus 2 to minus infinity. So any integer at all. This gives the wave function an integer number of half wavelengths within the allowed region, inside the box. We choose to eliminate the negative values for k sub n because sine of minus x equals minus sine of x. It's an odd function. And the wave function already has an arbitrary multiplicative value b. So the negative values for k sub n produce the same set of wave functions as the positive values. So we don't need the extra values of k sub n being negative. We don't need those to form a complete set of eigenfunctions. We're also going to eliminate the zero value for k sub n because it produces a wave function that is zero for all space at all times. This is the trivial mathematical solution of the differential equation that does not represent a physical particle state. Probability would be zero, no particle in the state. So we can eliminate the zero value for k sub n. This is a possible time to take a break. Now we have the general time-independent energy eigenfunctions and energy eigenvalues for a particle in a box in one dimension. Psi sub n of x equals 0 for x less than 0, b times sine of k sub n x inside the box from 0 to a, 0 for x greater than a, where we have the restriction that k sub n times a equals n times pi, where the quantum number n takes on positive integer values, 1, 2, up to plus infinity. We can rewrite this to move a on to the right-hand side. K sub n equals n times pi over a for n equals 1, 2, up to infinity. And now that we know k sub n, we know the energy eigenvalue E sub n. E sub n equals h bar squared k squared over 2m. And if we substitute the value for k sub n and rearrange, we get that energy equals pi squared h bar squared over 2ma squared times n squared. The energy values that are solutions of this time-independent Schrodinger equation, the energy eigenvalues for this particle in a box in one dimension, are discrete. They're quantized. They are not continuous. Therefore, this result is quantum mechanical, not classical. In classical mechanics, you could put a particle in any box and it could have any energy inside the box. Not here. Here, the box forces the energies to be discrete and quantized. The set of energy eigenvalues for a Hamiltonian is called its spectrum. There is a lowest allowed energy value, energy eigenvalue, and we call this the ground state energy. In this case, it's E sub 1 being pi squared h bar squared over 2ma squared. You should verify for yourself that this right-hand side correctly has the dimensions of energy. The lowest value of energy eigenvalue is more positive than the lowest value of potential energy for all space, which was 0. As we previously said, it must be. The ground state energy is not 0. The potential energy is 0, but the ground state energy is not 0. We say that there is 0-point energy, positive non-zero kinetic energy, for this and every bound ground state. I won't give a perfect definition of bound here. I think you can see that this particle is bound. It is bound in the box. But the definition of bound is a little complicated in general, and I don't want to cover that here. Why is the ground state energy not zero, not equal to the potential energy? Unlike the free particle, this particle is restricted. It's localized in space. The uncertainty in its position is finite, not infinite. In the free particle, the uncertainty was infinite. It could be anywhere in space, anywhere and everywhere. But here, it's definitely in the box. It cannot be beyond the box, so the uncertainty in its position is finite. By Heisenberg's uncertainty principle, there will be some non-zero minimum uncertainty in momentum. Therefore, momentum cannot be a single definite value. That can only happen when the uncertainty in momentum is zero, and it cannot be zero here. Since the momentum cannot be a single definite value, it cannot be the definite value zero. There will be some momentum, so there will be some kinetic energy, so the total energy will be higher, more positive, than the potential energy, and therefore positive, not zero. We will do these uncertainties more analytically in a coming lecture, not here. This is a possible time to take a break. The bound state energy eigenvalues E sub n can be expressed as the ground state energy E sub 1 times n squared for this particle in a box. So those energies are quadratic in the quantum number n. N can range up to plus infinity, so there is a countable infinity of eigenstates and eigenvalues for a particle in a box in one dimension. We count the eigenstates using quantum number n. There's no upper bound to these energy eigenvalues. They tend to plus infinity. However, this particle in a box is an idealized problem. The relativistic Schrodinger equation is no longer valid when we become relativistic and the energy approaches mc squared. And treating the potential energy as infinite hard walls, that will become unphysical, unrealistic at too high a particle energy. So it's a simple mathematical problem, but we have to be aware that there are limits in terms of where we can apply it. Now, there are no unbound states, also called scattering states, for the particle in a box. As high as we make the energy, it is still bound in the box until we no longer can use the Schrodinger equation. These energy eigenvalues are non-degenerate. Each energy eigenvalue corresponds to a single value for n and a single eigenfunction with arbitrary multiplicative factor. Eigenfunctions have an arbitrary multiplicative factor. Generally, we replace the factor with a single real value that gives the eigenfunction a probability of 1 for the particle being in that state. Then we say that the eigenfunction is normalized. I'll give the normalization here, and we'll verify the normalization in a coming lecture after we discuss probability. So the normalized time time-independent energy eigenfunctions for a particle in a box in one dimension, psi sub n of x, 0 for x less than 0. We'll replace the arbitrary multiplicative factor b with square root of 2 over a, and then sine k sub n of x inside the box, and then 0 outside the box to the right. Where k sub n is unchanged, n pi over a, n equals 1, 2 up to infinity. The energy is unchanged. The only thing I've done here is replace b with square root of 2 over a. Now there's a little bit of ambiguity in that I used to call it psi sub n. I'm still calling it psi sub n. The two psi sub n's are different. The first one was unnormalized and had an arbitrary multiplicative factor b. This one is normalized, square root of 2 over a, but I'm still calling it psi sub n. Now, I'm not doing that to be difficult with you. This is how books will do it and how classes will do it. What happens is at any given point, they need to tell you and you need to know whether you're dealing with normalized or an unnormalized eigenfunction. So that will happen in words, not in notation in the equation. So if you open to a random page in a book and you see a wave function, the notation of the wave function will not tell you if it's normalized or unnormalized. You need to either know or calculate it or verify it. This is a possible time to take a break. Let's graph the wave functions for n equals 1, 2, and 3. I'm not putting any numbers on the vertical axis here. So I'm showing the shape, but I'm not putting in numbers. So the horizontal axis inside the well is 0 to a. Greater than a is outside the well, and the wave function is 0. Left of 0 is outside the well, and the wave function is 0. But inside the well, the wave function is sinusoidal, as we saw. Let's look at the n equals 1, the ground state, the green curve here. It is a half wavelength of the sine function. So 0 at x equals 0, and then it gets positive values, and then it reapproaches 0 as we get to a, half wavelength. Now let's look at the n equals 2. Now, although I'm moving vertically here, don't think that this means anything. This has a new x-axis here. For n equals 2, we get 2 half wavelengths of the sine wave, or 1 complete wavelength. So sine wave goes up, crosses 0, goes negative, reaches 0. This 0 crossing, we're going to find that in quantum mechanics we call that a node. For n equals 3, we get 3 half wavelengths. Sine wave goes positive, goes negative, goes positive, it again hits 0 again at the right hard wall. And we have 2 0 crossings, 2 nodes. Now, we want to note a couple things here. These curves look like standing waves of a string. For example, a guitar string. The differential equation we had was the normal oscillatory differential equation, so yes, we have standing waves. The slopes of these wave functions are continuous everywhere except at the hard walls, x equals 0 and x equals a, where the slope is discontinuous. Let's look at this. What's the slope? 0, 0, 0, 0, 0, 0, 0. Oops, now the slope is positive. And it went from 0 to positive instantaneously, discontinuously at the hard wall. Now the slope is positive, positive, 0, negative, 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 and it jumps to 0 at this hard wall. So for all of these eigenfunctions, the slope is continuous in the left region, continuous beyond the box in the right region, continuous within the box, but discontinuous at both hard walls. In quantum mechanics for spatial problems, the spatial first derivative, partial derivative of psi with respect to x, it must be a continuous function of the spatial coordinate except at hard walls and also at potential energy impulse functions, which we're not going to cover. This is a possible time to take a break. As we increase the quantum number n, the wave functions are alternately even and odd functions of position with respect to the center of the box, the center of the well. Let's look at that. Here's the center of the well. This function is even with respect to the center. This wave function is odd with respect to the center. This function is even with respect to the center. A node is a location, point in one dimension, curve in 2 dimensions, surface in 3 dimensions, where the wave function crosses from positive to negative or vice versa. Hard walls are not called nodes. In quantum mechanics for spatial problems, a bound state ground state has no node. Bound state excited states, i.e. not the ground state, have one or more nodes. In going up in energy from one bound state energy eigenstate to the next, adjacent eigenstates with higher energy, the wave function gets one additional node. Adding the node reduces the distance between the zero crossings. This increases the kinetic energy and the particle energy. So the ground state has no nodes, no zero crossings, ignoring the hard walls. The first excited state has one node. It is a zero crossing. The second excited state, n equals 3, has 2 nodes, 2 zero crossings. Between the hard walls, where energy minus the potential energy is greater than 0, the wave function for particle in a box in one dimension always curves toward the psi equals 0 axis. Let's see this. Here the slope is positive, but it is decreasing, and the curve is curving toward the axis. Here the curve is curving toward the axis, and after the zero crossing, it's curving toward the axis again. Curving toward the axis, toward the axis, toward the axis. In quantum mechanics for spatial problems, the time-independent wave function, psi of x, curves toward the psi equals 0 axis in regions where energy minus potential energy is greater than 0, and curves away from the psi equals 0 axis in regions where energy minus potential energy is less than 0, called a classically forbidden region. Now, I should qualify this some because in this region, x less than 0, there's no curvature. Psi is 0, the particle can't be there. Energy minus the potential energy is less than 0, but it is minus infinity, and I should qualify that. So we have not yet seen an example where the energy minus the potential energy is less than 0, but still finite. Let's look at an example for which we have that. Let's look at the wave function for a more advanced problem called a finite square well. We're not going to do the math for this, but we can look at the result. So we have a box, we have a well, but in this case, we resize it and reorigin it so that the box extends from minus a to plus a, and the walls are finite, not infinite. So I'm not showing any crosshatching here. I could show the ground state energy, but it's more instructive in this case to show the first excited state, which is odd with respect to the center of the well, and it has one zero crossing, one node at the center of the well. This is a zero crossing. Within the well, we have a sine wave, but it's different than the particle in the box in that the sine wave does not match 0 at the walls, because these walls are not infinite steps in potential energy, they're finite steps. It's a finite well, and an aspect of that will be that the sine wave will not be 0 at these walls. And there will be a wave function, a non-zero wave function, outside of the well. That wave function will not be a sine wave, it'll be an exponential. In this case, well, let's look at the green one. In this case, it's a decaying exponential. The blue one here, it decays if we walk in the minus x direction. The regions outside this well are not completely forbidden, but they are classically forbidden. The energy that I'm using here is not enough for the particle to escape the well. So energy minus potential energy inside the well is greater than 0, and we have a sinusoid and the curve the curvature of the curve curves toward the axis. But outside the well, this particular energy is less than the potential energy, and the wave function here curves away from the psi equals 0 axis. This exponential curves away from the axis, and this exponential curve curves away from the axis. We're not going to do the math of this problem, but I'm showing it to you to show that in this case, the particle has some probability of being outside of the well in the classically forbidden region, and that the wave function there is curving away from the psi equals 0 axis. Now notice that the wave function is continuous at these walls, continuous here and continuous here, and also that the slope is continuous. The slope to the left of this wall is equal to the slope to the right of this wall. This wall is a finite wall, a finite step, and so the spatial derivative, the slope, must be continuous across it, and it is there and there. This is a possible time to take a break. Now, back to a particle in a box in one dimension. We have the time-independent energy eigenfunctions, the normalized ones, so we can easily produce the normalized time-dependent energy eigenfunctions for particle in a box. This is easy to do for energy eigenfunctions. Capital psi sub n of x and t is 0 for x less than 0. It's 0 for x greater than a. But in the region 0 to a, it is the time-independent portion, square root of 2 over a sine k sub n of x, multiplied times the time-dependent complex exponential, e to the minus I e sub n t over h bar. We can do this because it's an energy eigenstate, and we can solve the time-independent Schrodinger equation and trivially get the time-dependent energy eigenfunctions with this complex exponential, because this wave function has a definite energy, E sub n. So now we have the time-dependent energy eigenfunction, and we have k sub n, and we have energy E sub n for all quantum numbers 1, 2, 3, up to plus infinity. The set of eigenfunctions form a complete basis for solutions to the Schrodinger equation with this Hamiltonian. Any superposition state, so not necessarily normalized, not generally an energy eigenstate, that is allowed or valid for a particle in a box in one dimension can be expressed as follows. General superposition state, psi of x and t, equals the sum from n equals 1 to plus infinity of c sub n, and some suitable complex number c sub n that can depend on n and generally and always will depend on n, times the time-dependent energy eigenfunction capital psi sub n of x and t. So we know the energy eigenfunctions, but we also can have arbitrary superposition states. We will look at this in a later lecture, but not today. We'll see in a future lecture that this wave function is normalized if and only if the sum from n equals 0 to plus infinity of the complex conjugate of c sub n times c sub n equals 1, or the magnitude of c sub n squared equals 1. Remember, in general, c sub n will be a complex number. This is a possible time to take a break. Now, let's switch gears a little and let's use the particle in a box ground state energy, which we will calculate in electron volts, to get some insight into some other problems that we can consider confinement in space. Remember, I said that when I first learned about particle in a box, I gave it no respect. It's not a real potential, it's not a real problem, but it is a simple problem, simple mathematical problem. And I didn't have perspective to know why I should care. Well, one reason to care is because with very little math, we can try out different problems, different particles, different masses, different box widths A, and see what the energies would be. And actually, we can draw some physical conclusions about some problems that would be very complicated. And we can draw some generally useful conclusions about more complicated problems, some more complicated problems, without doing more complicated work. So let's see that. I wish that I had known this when I was first learning quantum mechanics. So we're going to take 3 different particles, an electron, a proton, and an up quark. An up quark is an elementary particle. The proton consists of 3 quarks, 2 up quarks and a down quark. We're going to take those 3 particles and we're going to do some particle in a box, one dimension, calculations and see if we can learn anything. Here are the masses of those particles. The proton is like 2,000 times more massive than the electron. The proton consists of 3 quarks. Pretty surprisingly, maybe shockingly, the quark mass is not anywhere near the mass of the proton. The quark's rest mass, if we could stop it and measure it, which we cannot, if we could, its rest mass is only like 4 times higher than the electron. And yet 3 quarks make up the proton, which has mass 2,000 times higher than the electron. Let's take the mass and express it as rest mass in electron volts. 500,000 electron volts for an electron, 900 million electron volts for the proton, and the up quark is 2 million electron volts. Now we're going to subject these to different confinements using particle in a box. So we know the mass of the particles. Now we need a column to tell us the confinement size. I'm going to express that as different diameters, but these will be A in the energy eigenvalue equation these values will be mass m, these values will be a in meters. This is a possible time to take a break. First case, let's take the proton diameter. 1.7 femtometers, 1.7 times 10 to the minus 15th meters. I've already done the math for you. You can, and I encourage you to plug in the values for M and for A and do the math. I'm not going to do it in this lecture. I just want to look at the results. So assuming I made no mistakes, the ground state energy eigenvalue in electron volts for an electron mass confined to a proton diameter would be 1.3 times 10 to the 11 electron volts. But whoa, this is almost 1,000,000 times higher than the electron's rest mass energy. So there's no way that this is a valid conclusion. We can't use Schrodinger equation. And if we ever get a result in the Schrodinger equation that is relativistic, then it was not valid to use the Schrodinger equation as a total way to solve that. So we did get an energy much higher than the rest mass energy. So it's invalid, but still instructive. Why is it instructive? It's going to be true that if you try to confine an electron to within a proton diameter, its energy, it's not going to be this value, but its energy is going to be so high that it is going to be relativistic. That is true, even though that we can't rely on this number. So that energy is going to be, that electron is going to have very high kinetic energy. It's going to be hard to confine that electron to a proton diameter. Now, okay, you could say, okay, well, who cares? Why do I care? Does this ever happen? Can we make it happen in a lab? Does it happen anywhere in the universe? We can't so easily make this happen in a lab, but it does happen in the universe. It happens in neutron stars. In neutron stars, protons and electrons are squeezed so close, so densely, so close together that the electron is confined to a proton diameter. But actually, having that much confinement, other physics kicks in and the electron merges with the proton to become a neutron. So, although we can't predict that from Schrodinger equation, the fact that this energy is relativistic tells us that something interesting is going to happen beyond the non-relativistic Schrodinger equation. Now let's take the proton and confine it to a proton diameter and see what happens. We get a ground state energy of 70 million electron volts. And although that seems like a lot of energy to us, it's less than a tenth of the proton's rest mass energy. So the proton doesn't really mind being confined to its proton diameter. It doesn't care. Now you could say, oh, this energy is pretty high, there's interesting stuff happening. This is like gamma ray energies. And we could say, well, gee, that's interesting. Maybe just confinement of the proton to its diameter could have excited states, and there could be some, gamma ray absorption or gamma ray emission. And indeed, this happens in nuclei, although maybe not necessarily because of particle in the box. But at any rate, this number is not relativistic for the proton. Now let's confine an up quark to a proton diameter. Its energy would be 30 billion electron volts, but its rest mass energy is only 2 million electron volts, this up quark would be highly relativistic if we confine it to a proton diameter. And in fact, that's what happens. The quarks are moving relativistically when confined to a proton diameter, and that kinetic energy is what gives rise to what we consider the rest mass energy of the proton. When we say the proton rest mass, we mean that the proton as a unit is not moving, but the quarks inside the proton are moving, and they have kinetic energy, and they give rise to the proton's high rest mass energy. Now, we could say, well, why do the quarks stay confined to the proton diameter anyway if they have to move with relativistic energy? And they stay confined because they are attracted to one another with the strong nuclear force, which comes about because of quantum chromodynamics. So, particle in the box says that an electron confined to a proton diameter would be relativistic, and up quark confined to a proton diameter would be relativistic, but the proton confined to the proton diameter, that's normal business as usual for the proton. This is a possible time to take a break. Now let's look at a different size, a larger size. We'll take the Bohr diameter, twice the Bohr radius, for a hydrogen atom, and we'll divide that by 100. So 1 angstrom divided by 100, 10 to the minus 12 meters, 1 picometer. What if we confine an electron to that size? Well, we would get an energy 3.8 times 10 to the 5th, which is pretty close to the electron's rest mass energy, so it would be somewhat relativistic, not strongly relativistic. We may or may not be able to use the Schrodinger equation. We may or may not be able to trust this number. There are some relativistic corrections we can do to the Schrodinger equation. So we're not going to do it, but if one wanted to, one could get a better number than this and still use the Schrodinger equation. So it's somewhat relativistic, but not greatly relativistic. So why should I care? Does this ever happen? Can we ever make this happen? Yeah, it happens. All heavy nuclei, the two innermost electrons, the 1s shell electrons, they are very tightly bound to the nucleus. And for heavy nuclei, they're bound about to this size, and so they do have slightly relativistic energies. And so if we wanted to calculate their energy levels, we should use the relativistic corrections to the Schrodinger equation. How about a proton confined to Bohr diameter over 100? Nah, its energy is very little. It doesn't mind, it doesn't care. Let's increase the confinement size, so less confined. Let's look at a Bohr diameter, 1 angstrom. 1 angstrom diameter, 10 to the minus 10th. For an electron, we would get an energy of 38 electron volts, so definitely non-relativistic. But notice, what should the electron energy be in a hydrogen atom if the electron is hanging around within half an angstrom radius of the nucleus? Well, we know the Bohr energy, ground state energy, it's minus 13.6 eV. This energy is positive. It's just because of where we set the zero. So let's compare this 38 to 13.6. It's in the ballpark. It's not true. It's not accurate. But here we use just an infinite square well, a particle in a box, and we said put an electron in it, and let's set the box size to about what the ground state of a hydrogen atom has. And we did it in one dimension, and there was no hope really of getting a truthful answer to the hydrogen ground state energy, but we were only off by a factor of 3. That's pretty amazing and worth giving a little respect to this crummy particle in a box potential that was easy to solve, and we knew it wasn't physically true for any real systems, but it's not bad for the hydrogen atom. Now, if you put a proton and you restrict it to the diameter of a hydrogen atom, its energy is very small. It doesn't care. Now let's give the electron bigger boxes. 10 angstrom. When we change the confinement by a factor of 10, we change the energy by a factor of 100. So we go from 38 to 0.38, and if we make another factor of 10, we go to 3.8 times 10 to the minus 3. So these energies get small as we increase the confinement, and so and I don't think I want to say more about that. Okay, now let's look at two other cases of confinement. We previously looked at a 1 micron size bacterium with mass 10 to the minus 15 kilograms. We previously, in another lecture, we looked at its de Broglie wavelength and said, well, de Broglie wavelength is so much smaller than its size, it's definitely classical. Well, now let's look at its particle in a box energy. Let's confine that 1 micron sized bacterium to a 1 micron sized box. We can calculate the particle in a box ground state energy. We get 3 times 10 to the minus 22 electron volts. Way negligible. It behaves classically. We don't need quantum mechanics for the motion of a bacterium. Now let's confine a baseball to a box about the size of a baseball, 10 centimeter box. Its ground state energy is 2 times 10 to the minus 44 electron volts. Infinitesimal, can't even be measured. It definitely behaves classically. So I would like you to remember particle in a box, and I would like you sometime, if you have some more complicated problem and you want a first cut at its behavior, feed it into particle in a box and see what the behavior might be. This is a possible time to take a break. We're almost done with this lecture. Now let's compare the energy spectrum of particle in a box to two other potentials, which we're not going to solve, but it will be useful to see the difference. On the left, we have particle in a box in one dimension. The particle is between 0 and A. This black line is the zero energy, potential energy. Ground state, E sub 1. Excited states, the energy E sub n is n squared E sub 1. It grows quadratically in the quantum number. 1, 4, 9, 16. Spacing gets bigger as we go up. Here's a different potential. one-dimensional simple harmonic oscillator, abbreviated SHO. Its potential is quadratic in position. Position horizontally, 0 of position, x. Potential is 1/2 mass times an angular frequency, omega, squared, times position, x squared. So this black curve is the potential energy. This is a pretty magic potential. We're not going to solve it. Every book solves it. Every class solves it. With this potential, the energy levels are equally spaced. The ground state energy is not 0. It was not 0 in particle in a box either. There was 0 point energy, and there is 0 point energy here. These curves are not to scale of one another, neither horizontally nor vertically, so don't look at scale. Energy is h bar omega times n plus 1/2. N equals 0 is the ground state. Ground state energy is h bar omega over 2. To get to the first excited state, n equals 1, we add energy, h bar omega. So we end up with h bar omega times 3/2, then 5/2, 7/2, and so on. Energies equally spaced. Which means that when we go one step in energy, if we go one step in energy up, we have to absorb a photon of energy h bar omega to do that. If we go one step down, we emit a photon of energy h bar omega to make that transition. We're not going to show the wave functions here, but let's look at this n equals, we'll look at the n equals 0 ground state. It's going to have a wave function between the here and here where the potential is. It's going to have a wave function which has no nodes because it's ground state and is curving toward the psi equals 0 axis. But then if we take this energy and we go to the left of the potential energy curve, energy is going to be less than potential energy, but the particle can exist there. It has non-zero probability to exist there, but the wave function will be an exponential that curves away from the psi equals 0 axis. Now, this is interesting mathematically because it produces equally spaced energies, and it's the only potential energy that will do that for the Schrodinger equation. It's also interesting physically. This harmonic oscillator potential, we get this potential when simple systems are able to vibrate. Molecular bonds can vibrate. And this potential is approximately true, at least for a ground state, and maybe the first excited state, for vibration of molecular bonds. So this energy, h bar omega, we may see this as an absorption energy or an emission energy for a molecular bond. And the energy will depend on omega, and omega will depend on the physics of that bond, the bond strength, the bond length, the masses of the atoms or units on both sides of the bond. So omega is generally going to be a unique indicator of which bond absorbed that energy or emitted that energy. So in a laboratory, we can learn the omegas for different bonds and different molecules, and then in astronomy we can look at the light that comes at us, and we can sometimes find certain molecular bonds, certain molecules in gas clouds in the galaxy. These vibrational energies for molecules tend to be in infrared range, and we can see infrared. We can see some infrared from ground-based telescopes, but the atmosphere absorbs a lot of infrared frequencies, so we can also have a infrared telescope on a satellite. We can see molecules, water molecules, carbon monoxide and dioxide molecules in gas clouds in the Milky Way, and we can also see some simple and even not so simple organic compounds in gas clouds. So some astronomers, their whole career is focused on infrared astronomy of molecules. This is a possible time to take a break. Now here's a different potential. Here's the potential for the hydrogen atom. We've seen this before if you've done the lecture on the Bohr atom. This green curve is the potential energy curve. This blue curve is the binding or total energy curve. The potential is proportional to -1 over R. The ground state energy, n equals 1, is minus 13.6 electron volts. The general formula for the energy eigenvalues is minus 13.6 eV over n squared, where n is the principal quantum number, and this does not cover relativistic corrections. So for n equals 1, we had minus 13.6 eV. For n equals 2, we have minus 3.4 eV. For n equals 3, we have minus 1.51 eV. N can grow to be minus infinity, but notice that here, as n grows to positive infinity, the energy, the binding energy, approaches 0 from below, from negative values. So this has a countable infinity of bound energy eigenstates, but this countable infinity is in a finite range from minus 13.6 electron volts up to 0 electron volts. For both particle in a box and simple harmonic oscillator, the energy levels were a countable infinity of energy levels, but they had no upper bound because the potential grew to infinity, so there was no upper bound to the energy eigenvalues. And so there were a countable infinity of bound states, and there were no unbound states, no scattering states for these two problems. But for the hydrogen atom, if we gave that electron positive total energy, it would have enough energy to escape the binding of the nucleus, and it would then be in an unbound state, a scattering state, and there's an infinite continuum of unbound states for the hydrogen atom, for the electron in a hydrogen atom. We're not finished with particle in a box, but the next lecture we'll do some general quantum mechanical properties of wave functions and energies, now that we've seen some concrete example, we can go back to some general properties, and we're also going to introduce probability and measurement and uncertainty, and then we'll return to finish particle in a box once we have learned about probability, measurement, and uncertainty. This is the end of lecture C3.